Okay, good morning. How are you? Any exam done already? Not yet.
Static quiz.
Statics quiz. What about calculus 3?
No.
Not yet. Okay. I saw your homework and you are using symbolic manipulator, yeah? The SYMS. Did I teach you that already? SYMS? No. Where did you learn that?
Actually,
ChatGPT?
yeah.
Okay. So you saw that. Yeah. Okay.
I don't know how to substitute. So I asked him.
So you asked the ChatGPT.
Yeah.
Yeah.
Then they show me the use it.
Okay. So you learn new things, right?
Yeah.
Yeah. That's good. Okay. Today we will focus more on the differential equations. Before that, I want to discuss the homework solution, but with different method. Yeah. If you plot the velocity, you will get this curve. Yeah. So let's say from 0 to about 2.3 or 2.4, the slope of this curve is negative. Yeah, facing down. So the slope is negative, which is why when you take the derivative of the velocity, you get negative value for the acceleration. Yeah, and at this point, when it is at the lowest point for the velocity, the acceleration becomes 0. Okay, so that's what you also have to see in your solution. Yeah, the diff that I'm using is just diff without SYMS. Yeah, you see here, I'm just using the diff. Do you know what's the difference between your diff and this diff? Anyone know? Your version of diff, you take the analytical solution of the derivative. Yeah? Sorry? The result of my diff is an array. To be exact, is an array. How does this doing its job then? The diff? Yeah, it is taking the difference. So let's say if you have an array X of A1, A2, A3, A4, then let's say you are writing diff of X, then the result would be A2 minus A1, and then A3 minus A2, and then in here A4 minus A3. That's what the diff do in the MATLAB. Yeah. So what this thing here? What does it say here? If you plot X, let's say you have the X in here, and this is your A. Yeah, A1. No, sorry. This is not A. A is going up. A1 here, A2, A3, A4. Okay. At the first point you get A1. Let's say in here you get A2, maybe A3 around here. That's A4. So what is A2 minus A1? In this case, it's what? It's this, yeah, the distance between A2 and A1. Meanwhile, A2 minus A3 is this one, yeah. So if I know what's the distance from here to here, and then I take, let's say this is A2 minus A1 and this is delta t, let's say. If I do A2 minus A1 and then divide by delta t, what do I will get? It's the gradient. Okay, exactly what we need, gradient. So if I only give you an array of the v velocity without giving you the function, you cannot do using your method, correct? Yeah. So you have to use this. Do you understand the situation? Yeah. So let's say if I give you an examination, I give you the array, not the function. Then I ask you to get the derivative of that function. Then you use this. Is this clear or not clear? David, is it clear? Yes or no? Which one? Not convincing. uh, please tell me if you still don't get the method. No one asking why I divide by 0.01? Huh? Yeah, that's the delta t, yeah, correct. That's the actual delta t that we have. If we don't divide by this one, which I specify here, you will not get the correct solution. And then what else that you don't know here? Sorry. I think I made a mistake. Is this the one? Oh yeah, this is correct. Yeah. Any question on line 7? Yeah, why don't you ask that? Any idea why I don't use T? I use TA instead. Any idea? Okay, what do you notice here? The what? The lengths are different, yeah. We have 4 elements here. In here we have only 3 elements. So in here, the elements of V and A is different also. Different by 1. Let me say this. Let's say you have a velocity which says it is equal to t. Velocity is equal to t. And you want to find out the acceleration. Mathematically, this is which is 1, yeah. And then you want to plot the v. You plot v at t equal to 0. What is the velocity? 0. So it goes like that. What about the acceleration when you plot it? Constant, like this. So this function has derivative as this one. Really? Okay, let me ask you, what's the velocity of this when t is less than 0? Do we have any velocity before the 0? Yeah, for physical system we don't have. Okay, it's like yesterday's thing, yeah, something that's done yesterday. So in here we have nothing to discuss. Okay, meanwhile when you put the acceleration in here, the derivative at 0 cannot be defined. You get what I mean? Yeah. The requirement for a derivative, whether you can take a derivative of function or not, is that when the function is continuous. Do you learn that in calculus? Yes. So this function at 0 is not continuous unless, where's my my other, oh, it's this one. Why don't you tell me? Unless your function is like this, okay, go all the way, and then you can have this, yeah, continuous from minus infinity to plus infinity, then you can have this. But then at zero, it's not there. So at zero, the acceleration cannot be defined, which is why I start from 0.01 in this case. Okay. So your solution that you have, you will have acceleration at zero. Why am I laughing? Because you are wrong. Analytically, you are still wrong in that case. Yeah, velocity cannot be defined at zero. Okay. Yeah, now you learn it. So this is the result. Yeah. Oh, why the result is not 2, yeah, not minus 2, but minus 2.03. Huh? No. Even if I move to 2. If x is, let's say, 1.9, is it 1.99? Yeah, 1.99. I will not get minus 2.03. I will get minus 1, more than 2. Oh no. So because this is a numerical solution, you will not get the exact answer as you did using the sims. Okay, this is numerical solution. Now we get into the business now. MATLAB is used to compute the numerical solution. Okay, so in many cases you will get error like this, and it is acceptable. So don't get surprised if your numerical solution is different with the analytical solution, and that's because of the increment that is not small enough. How small we can reduce the increment to? Any idea? Yeah, if from 0 to 3 with this increment, I have 300 data. Okay, I push more to the, let's say, 0.001, I will get 3000 data. So what can you see here? So you see, yeah, I cannot see it. Let's say I push it to 0.01. Wait. Yeah. So if I do that, I will get this result. Can you see it? If I reduce the increment to 0.01, I will get, wait. I have to divide by 0.001. Sorry. This one. Yeah, you see it? It's minus 2.003 compared to this one, yeah? Compared to this, okay? So when I push the increment smaller and smaller, then this number 3 will go beyond, okay? Further go away. So you can make it pretty close to -2 if you keep reducing the time increment. You are not happy with it? You don't seem to be happy, right?
Let's go.
No, this is the reality of numerical computation. If you don't like it, don't go into mechanical engineering. Forget about it. Go into maths department. I'm serious. I'm serious. If you don't like numerical error like this, just quit ME now. Go into math department, physics department. Physics still do simulation also. No, just go to the math department. I'm serious. You go, let's say you take a capstone project with Pafarid, and then you want to design a chair, let's say, a simple thing, chair. And then you want to compute the stress experienced by the chair. Are you able to do that by hand calculation for a complex? Well, I challenge you, really. And then you go into finite element analysis software, let's say ANSYS, Abacus, COMSOL. You will get numerical solution and it has error. So if you cannot accept that, just go.
Walk out.
Yeah, just walk out from ME.
Oh, you don't understand nothing.
So like I said also to the last year students, accepting the error that you have in the computation is one of big step you have to take in taking mechanical engineering, especially the MATLAB course. Okay, and then you have to deal with it. Can you make the increment to be 1 to the 10 power minus 1 10 to the power of 30, let's say? Very small increment. You can destroy the computer. Only for a simple calculation like that, your computer will hang up. Not enough memory. You don't seem to like it, the idea. I can see it from your face that you don't like the idea. So yeah, if you still want to stay at ME, I can give you a solution. You take capstone project with me in control system design. You do theoretical analysis and then prove your concept. No simulation at all, just make theory and then prove it mathematically. I will show you my paper. Yeah, my paper. This is how I do it.
Sembilan. Kelamaan.
9,4.
Itu yang resistif. Malah langsung cepat amal. Enggak.
Ya, tadi.
Orang nggak nyampe tapi mau.
Oh, okay. Can see it. So this is one of my work, and I deal only with math equation. Okay, where is it? So my job here is that I first define a system using state space equation, and then I state some assumptions, and then I said here the goal of the work. Okay, what is my goal? So I stated here. Yeah, that's the goal. And then in the main result, I am stating my strategy. How do I achieve the goal? Okay, so these are all the strategy that I devised. After I said all of that, okay, I need to use some lemma to prove my theorem. Sorry, this is the control input. Sorry, my control input is here. Okay, this is my proposed control input. So I have to prove that this strategy is working. Okay, so I make another assumption in here. And then the theorem is here. Yeah, that's the theorem. Okay, what is a theorem? A theorem is just a statement. Okay, a statement. Let us see the statement. So the statement says, let's say I have this kind of system, and then I have this kind of assumption on my system, and then I propose something that I can apply to the system. Then I will achieve this one, and that one. Okay, after that, I have to prove it. Yeah, after that, I prove there is no picture at all. Yeah, not yet. So some simulation is done only to show the result, but that's not the point. The point that the reviewer look is the proof of my work, which is where is it? I put it at the back. Yeah, this is the proof. So this is all of them are statement, and then yeah, logical statement lah. So that's one way that you can do. Let's say you don't like numerical simulation, but you still want to stay in ME, you take this. Yeah, I believe only 2 students so far in ME that takes this kind of topic. Only 2 students. Yeah, but numerical simulation also nice, nah? Yeah, because when you want to visualize how the system works, you still need the numerical simulation.
Gross minus udah main aja itu saya enggak sih ya aja nggak mau bantu gampang
Okay.
bisa sendiri sampai suruh
So for those who don't like the numerical solution results, when I give you an array in the exam and I ask you to find out the derivative of that array, don't use the diff. You don't like the numerical solution, right? So when I give you that problem, don't use the diff. I don't know how you want to find a solution. Okay. You have to tolerate the error, because not all of the problem can be solved analytically. Not all of them. Yeah, human have their own limitation. Okay. So I've discussed this over there, yeah. Okay. Let's discuss about differential equations. What's your idea last week about the differential equation? Yeah, pure integration. Let us remind ourselves if this is, and then x dot is actually dx over dt, yeah, and then this is 5 of x. I remove the t because we know that x is a function of time. So how do we do it? Okay, you move with here. So we have 1 over 5x is equal to dt, yeah. Oh, negative. Okay. So you integrate this. Let's integrate using different color. How do you integrate these two? This is from where? From what? X0, not 0? Ah, okay. This is from x0 and then this is up to x. What this is called? This is the initial condition, yeah. Initial condition. This one? Yeah, from t0 to the t. What do we get here? Who are you? Are you in this class?
MATLAB.
Oh, engineering graphics, is it?
Yeah.
Okay, what's the result of this integration? Okay, ln x minus 5, negative 1 over 5, and then ln of x. Okay, and this is from x0 to x. What about this? So it's just t minus t0. Okay, we just substitute the solution. So we have minus 1 over 5. This is ln x minus ln of x0, which is t minus t0. Okay. We will move this one to that side and also this one to that side, yeah, because we want to get what is x, right? X is something, so we have this ln x minus ln x0, and in here I have minus 5 t minus t0, yeah, that one, and then I put ln x0 to the right side. It becomes and then plus. Okay, then what's next? What's e? Okay, we do the exponential. So all of them left and right, we take the exponent, yeah. Okay, so what's next? I write here. What's next? This is equal to what?
X0 times e to the negative.
Let's do this first, yeah. E of ln x minus 5, and then multiplied by, okay, this one become x, correct, and this one becomes, leave it, okay, leave it, and then yeah, this is x0. So that is the linear ODE solution, pure integration, no MATLAB involved, yeah. Guessing function. What do I mean by the guessing function? In here we have the x dot equal to minus 5x. And we guess from the very beginning that x of t is e minus 5 t, and then this is the x0. So from the very beginning, we say that this is the solution. Then after that, we show that the x dot is just minus 5 times x. How do we do that? We want to show that the x dot is that one. So what do I do? What I will do is that I will take the derivative of this one. Yeah. So what's the result? Minus 5 down, and then this is still, so I will get minus 5 times, this is the x. So my solution is correct. I'll just have to show my solution and the original differential equation match up, just like you compute the derivative and the integral. Okay. Let's say you are doing the pure integration. If your ODE is like this, yeah, this is the ODE. X dot is ax, and x is a vector x1 up to xn, and a is a matrix. This is a1 1, a1n, or okay. Can you do this? Why? Let's say this is the matrix. In this step, what we do is that we bring out the constant to the left, yeah, by doing 1 over something. If we do this here, what do we have to do? Inversing of A. Okay. Do you want to compute the inverse of 100 by 100 matrix analytically? Yeah, you want it analytically, right? Come on. Huh? No. You are challenging yourself for analytical solution, right? You don't want to use MATLAB? Okay. The first thing is that when your matrix is very large, analytical solution will take forever. Okay. Until you graduate, maybe you haven't finished it yet. That's one thing. The second thing is that, do you know that not all matrices have inverse? Yeah, singular matrix doesn't have inverse. So pure integration doesn't work for matrix problem. It doesn't work. Do you want to say something? Huh? So when your problem is matrix, guessing method works. You can still use this method. Let me show you. So pure integration cannot handle all of things. Yeah. So we have what matrix, yeah, x dot equal to ax. And then I said my solution is this one. That's my solution. So my x dot is this one. So I will have A times this one again, yeah. You see, the pure integration lost to the guessing function. I haven't even used MATLAB yet. Okay. Sorry? No, the guessing is based on this, and then we know for scalar solution, the solution is that one, yeah. It's coming from this, and then we know for the matrix solution we can also apply that. You just have to try, then it works. Okay. Besides the guessing function, I have another method of solving the differential equation. No, not even MATLAB yet. Not yet. Not yet. Use the Laplace transform. This is also analytical solution. Analytical, but then you can simulate the system using MATLAB. Okay. How do we use the Laplace transform? Let me show you using Laplace transform. Hey, by the way, do you enjoy this kind of delivery material? Only that side. I don't believe you. This side. Is this okay? The delivery? Yeah, I want to show you that you need MATLAB. You know.
Yang ini disekat.
That side. I skip that guy. Those group we skip it.
Di paling ujung negligible.
So we have the x dot equal to minus 5x, and then we convert this into MATLAB. Sorry, a Laplace transform, yeah. So in Laplace transform, x dot becomes s times x of s, and the x is just plainly this one. Okay, and then actually I have to say that this is minus x0 in here, minus 5x of s, yeah. So the Laplace transform from here is this much. Okay, and then we want to find out the solution of x, yeah. So we have to group x of s. In here the function is in time, in t. In Laplace transform the function is in s. So from t we convert into s. Okay. I have x of s, and then this is s plus 5, and that is equal to the x0. So my x of s is x0 over s plus 5. Yeah, and it turns out the xt is the Laplace inverse of xs, and that is the Laplace inverse of this one, yeah. So we check into the Laplace table. The result is, what do you think? Surprisingly, it is e minus 5t x0. Yeah. So the Laplace inverse of 1 over s plus a is e minus at. So we use this pair, we get the solution. And by the way, the pair is derived also from the integration of the Laplace transform.
Wow.
Yeah, there are other advantages of why we use the Laplace transform. The first thing is that you can simulate system when you have Laplace transform. and I want you to install Simulink for next week. In fact, I have defined a homework, yeah. Not yet, not yet. Later, after this class, the homework for next week is that you have to install Simulink on your MATLAB. It's an add-on, so you have to install add-on, yeah. Install it,
Add-on.
and then it can also be used for control system design. I will give you an illustration. Let me give you an illustration.
Lu gila nih yang nggak pakai otak kan? Otak itu apa cuma pencet jadi. Mungkin lu suka nanya-nanya. Nanya gara-gara ada dot yang nggak kelihatan di segala. Kalau nggak juga jadi.
Okay, guys. You see here. Let's say you have a car. This car, yeah, and then the car runs on the highway, expressway, yeah. How does the car runs? The traction is developed here, yeah. There is a traction on the driving wheel. There is a traction, okay. And then let's say you want to make a system so that your car and the car in front of your car has a desirable distance. Let's say you want to keep the distance to be 30 meters, let's say. You want to keep it 30 meters, but you don't want to use your foot and your brain to do it. You want to ask the computer to do it. How are you going to achieve it? Any idea? Sensor.
If then else.
Huh?
If car more than
Yeah.
If distance less than 30, press brake atau nggak release gas.
Now you ask the system to do it. How the system can? How can the system do it? You have to delegate the regulation of the speed and distance to a system, right? Let's say I will leave for 30 minutes from here, and I want you to keep the class in order. Okay, what do I have to do? Yeah, I want to ask you to keep this class in order. Yeah, what I have to do if I want to ask you to do that? No. Yeah. Yeah, I want him in charge. How do I do it? What do I have to tell him? Replace. Just that?
You're in charge. This is the material. This is what you need to do.
Is that it? More. Correct. Give instruction, yeah. The instruction, let's say, Brandon, if this thing happen, you do this. Okay. If this thing happen, you do this. Don't do this, don't do that. That is a set of instruction. Yeah. Okay, the same thing you do to your system. You design a set of instruction, just like my paper. Yeah, that's actually a set of instruction. Oh yeah. The last method, Euler method, I will discuss this some other time. So I will discuss about this spacing control of car. Yeah, how do we achieve that? We said that we have to give a set of instruction to the car. This is ego car, to keep a safe distance with the lead car. The first thing you do, you derive the equation of motion. You draw the free body diagram. You have rolling resistance. In real case, you will have wind disturbance. Yeah, what's the wind? Yeah, what's the drag force of the wind? Yeah, it depends on the velocity squared, yeah, which makes the problem non-linear. So you get the Newton's second law, and then we convert into Laplace transform. Then we get what we call as the transfer function. So over here on the right side, we have transfer function of 1 over ms squared plus cs. The m in here is the mass of the car. And then the c here is the rolling resistance constant. Okay, the z is the displacement of the car. And then the t here is the traction. So the displacement of the car depends on the traction and then also the transfer function of the car. Do you know how to derive this? In physics, you are not taught on this one? Yes? Yeah, just m equal to ma. This is the acceleration, yeah? Mass times acceleration. And then I just have to explode or expand. What is the forces? These are the forces. And then after that, I convert this into Laplace over there. This is my transfer function. What you can do with Simulink is that you put this in the Simulink. So next week, you will learn about Simulink. Install Simulink, then you can do this. Yeah. So this is called the block diagram. Yeah, the block diagram, this is the control strategy. The plant, the transfer function is here, yeah. The transfer function that we created, we put it here, and then we have a controller behind it, and then this is the displacement coming from the leading car. So there will be a measurement. You say it's sensor, yeah. You measure the distance between your car and your lead car. So you do this. This is already a control system approach, okay, which I said previously. And this is the interface that we have in the Simulink. So you drop down the transfer function block there. You just insert what is the mass and then the rolling resistance coefficients. And then you put a controller behind it. After that, you simulate the problem. See whether your strategy works or not. And one of the response that you can see is like this. The purple color one is the desired distance, and the black one is the actual distance. So after some time, it reaches the desired distance. Yeah, so with correct instructions, you can make the car to go with what you want. And that's through the Laplace transform approach. With the pure integration, we cannot do that. Sorry. Yeah. Sorry. Yeah. Capital Z is the displacement. So in time domain, all of the variable a variable that is depending on time, it is lowercase. Yeah, when you convert into Laplace, it becomes uppercase. Okay. So Z dot here is velocity. Z is just displacement. So over here, Z capital is displacement, but in Laplace domain. Okay. Yeah, you don't have to understand about Laplace transform in complete term, but you will learn about using Simulink. That's what you will learn. Okay, so that completes our class, and that's the homework. Install Simulink, and then you have to try one of the Simulink examples. Analytical thing, you have to good at it. Numerical solution, you have to also be good at it. Yeah, doing design, all of them, that's mechanical engineering. Yeah, so analytical analysis is just one part of ME. So you have to be good at all of those area. Yeah, I can do design, I can do experiment, I can do mathematical approach also, numerical simulation. So all lecturers also like that. Okay, so don't just focus on one thing. Any questions so far? The interesting thing comes when we discuss nonlinear ODE. When you do the pure integration, the steps are quite long. And then if the problem involves more than sign term, then the derivation takes longer and longer. So this will come later when we discuss the Euler method. Okay, when we discuss Euler method, we will try to handle the nonlinear ODE. Okay. So next week Simulink, and the week after that we discuss the Euler method. Yeah, see you again.